already has a topology, any topology that you have in it, then you can look at continuous functions from the object to the field, if you put some topology on the field. And there's a problem here. What topology? You can put many topologies on the field. There are some canonical ones. For example, if you would use the Zariski topology, looking at it as an affine space, that you can look at finite complements, you can look at real topology if the field is real, and so on. So this corresponds nicely to complex varieties and algebraic and analytical geometry. Mixed and complex varieties have both structures. Okay, so if this topology is any topology, you don't even know that the polynomial, that the coordinate functions are continuous. Right? That is not necessary then. If I take a sort of canonical, my finger is not long enough. It has a strange shadow, commutative shadow that I can use this thing. So this topology could be obtained in some canonical way from the embedding, of course, for example, but also in a more intrinsic canonical way, as we will see later by some representation theory, which I will delete, as I said. Okay, so once you have a topology, you can look at relations between open sets and inclusion or conclusion, containing relation, and you have restriction morphisms from the continuous functions on the first to the smaller one. Another phenomenon that appears is that you can take, once you have topology, you can take neighborhood filters. If you have points, you have a point, you take the filter of neighborhoods, and then you get stalks by just taking direct limit of these rings of continuous functions, or whatever functions you actually want to look at. And that is a correspondence between a kind of points and a kind of rings. So via the filter of neighborhoods. I'm just repeating a little bit the classical ingredients of scheme theory, so that you see where the non-commutative theory comes from. So with such a situation, you find a ring space, which is open sets in a topology, and on every open you have something that maps from U to K, continuous in some topologies. And how these topologies arise for the moment is rather arbitrary, but of course if you know the Zariski topology you can think of that. So there are restriction morphisms, rho, that are the restrictions from U to V. Okay. So there's some observations here. If I would take an arbitrary topology, I can make the embedding. The embedding can be a pointwise embedding. I can just make an embedding of the geometrical object because I have points. I can embed it pointwise, and it doesn't mean anything topologically. So if I take an arbitrary topology, then, as I said, coordinate functions need not be continuous. So if you want to put a topology on the object, perhaps you should relate it to the topology on the field that you already have, if you have one. Otherwise, you first put a topology on the, first take a field, then a topology, and then try to connect these topologies. So if everything is nice, you want that if you apply this to the object, the affine space of K itself, then that should be your topology, perhaps. So, and this happens for the Zariski topology. Then there is a third problem, which is interesting, that you can reconstruct points from the knowledge of the locally ring space, from the ring space, and the restriction map. So the pre-sheaf or the sheaf information, that is what is given here, I will come back to that, should define the points. You have to reconstruct the points from that information. So that's, I'm stressing certain points that usually in commutative algebraic geometry people don't stress so much, because they're understood or automatic. But when you do the non-commutative version, this is essential, right? Because maybe I don't have enough points, for example, this will be the case. So this reconstruction of points from sheaf theoretic information, if it works in the commutative case, good. If we can use sheaf theory later in the non-commutative case to do similar things, or even better. That's why I defend the point of view that using sheaf theory for non-commutative geometry is okay. I know that Alain Kahn has said, oh, you cannot use sheaf theory for non-commutative geometry because it's a much too commutative technique. But I talked to him in Stockholm at one of the non-commutative geometry meetings, and I said, but on a non-commutative topology. And then he immediately said, oh yeah, I talked about topos. And since the word topos has been used, when I do the non-commutative version of this, it will not be a topos, it will be a non-commutative topos. And therefore sheaf theory is non-commutative. Okay, so trying to make it real compared to what? The title of the song was compared to what? Les McCann and Eddie Harris in the Jazz Festival of Montreux. Have a very good version of this. So we want to make it real. We have the fields there, and but what are you comparing to really? Where do you want to go? And here is the representation theory that I will delete. But I first will, before deleting it, so this is the good thing about deleting. First you have to say what you delete. This gives you a chance to talk about it. So I put this representation theory in a much more general frame than what you usually see. Usually you see about the representation theory of one algebra. I'm representing a category. I'm not really going to talk a lot about it, because there is a version of this kind of Grothendieck representations, I call it. Grothendieck is not to blame for that. Just in anyone, I couldn't find anything better. In a sense, you have a category, and to every object of the category you associate another category. So, and that other category is a nice category. So you can think of category of rings, and to every ring you associate the category of modules. Standard example. So for a ring R, let's call it rep R, representation of R. Not be necessarily the modules, but a Grothendieck category or an Abelian category. You can generalize. Bob will certainly see a lot of nice generalizations. I want to mention at least one. Instead of modules, you could take graded modules and you could do the projective geometry. That's an important one, which appears as a quotient of this one. So you have a system of ring morphisms, for example here. Lots of rings, lots of morphisms. You have a corresponding, so the rep is a functor. From the category of rings to a category of categories, if I can say that. That's not so bad, you can give this a meaning. And to every morphism respects the, in the case that I'm talking about rings, I can do more general things. In the case I'm talking about rings and ring morphisms, these things are restriction of scalar functors. You just restrict the scalars. Well, if this rep R would be modules, then this is the real classical restriction of scalars. So you have not one object represented, you have all the objects represented in some coherent way respecting the category structure. And this is a theory that it's published in the Journal of K-Theory a number of years ago with a student in Darisha. Oops. Okay, so once you have Grothendieck categories, there is many things you can do. But you can also do this with additive categories, for example, if people are interested in. You don't even need the additive, you can do very general things if you want. But for this talk, I think I can just as well. You may think modules, right? Or graded modules, depending on your philosophy. As I said here, you can take the graded modules or the modules. Graded modules will give you some kind of projective geometry, the modules will give you affine geometry. So in a sense, the choice of representations defines the geometry. The commutative geometers will never explain to you where the Zariski topology comes from. It comes from this choice. Because I'm going to show now how a canonical topology follows from the choice of the representation category of the category that you look at. So what can you do when you have a Grothendieck category? So one of the, I'm not sure, well, you can interact, curse, or ask questions. So I don't want to stop after 45 minutes and have a discussion, unless nobody asks any question, but you can interrupt me wherever. And if I have to explain something more, I'm willing to go anywhere. So when you have a nice category, there's a theory of localization theory for this category. Classically, certainly for Grothendieck categories, this is very well known. This torsion theory, some people call it Serre Gaussian categories. You have a lot of things, capital L filters. Many things are equivalent here. Radicals, torsion radicals. For the moment I will not explain more, but if you want, I could. For example, in the second lecture, there is one. So, if I take this category rep, R, the representation theory, and I take